What you do? Oh, you can keep recording it. I just have to say, for those people that went to David Held's talk, when he said RL meaties, that was one of the funniest things I heard. So when you're presenting that, it just made me laugh. Anyway.
All right, so this RI Aristotle. All right, so this talk is going to be about logical reasoning as mathematical programming, and let's start. So the outline of this talk is going to be as follows. So first, I will talk about the utility of logical reasoning. I'll then talk about the utility of mathematical programming. And I'll introduce the project that is the main core of this talk. And I'll talk about some initial ideas. So logical reasoning. Back in the day, there was a scientist called Aristotle, and he was a very prolific author. So in ICRA 350 BC, he published a paper called Prior Analytics. And in the paper, he made a quote, which I'm going to read. It basically says that a deduction in a discourse in which certain things being supposed something different from the things supposed results of necessity because these things are so. And it might seem gibberish to you, but I was actually talking about a tool which is called syllogism. So what exactly is syllogism? So syllogism is basically a device or a tool in formal logic, which basically makes deductive reasoning about a specific proposition based on certain facts it assumes to be true. And so what does this mean? If I give you a syllogism, which is basically if A equals B and B equals C, then A is equal to C. This can be thought of as a syllogism. And it's a valid argument in that if the assumptions that are being made, basically if A is equal to B and B is equal to C, then you can make the logical conclusion that A equals C. So you can think of this as a logical argument, but what does it actually mean in the real world? In order for you to get what exactly a valid argument means, you need to provide some grounding. And grounding essentially means providing context to a logical argument or a valid argument. And you're going to see grounding a lot in this talk, and so you should get that definition. And so once we ground this valid arguments, one way to ground it is using numbers, because numbers were invented because we wanted to come up with a representation of the real world. And so numbers help us to actually reason about things that happen in the real world. And so if I were to ground this syllogism as using numbers, we could replace the variables in there with numbers. So I could say if 0 is equal to 1 and 1 is equal to 2, then 0 is equal to 2. And based on the assumptions I made about 0 being equal to 1 and 1 being equal to 2, you could think of this statement as a logical statement because it essentially follows all these assumptions that are being made. But if you know anything about math, you know that this is not true because 0 cannot be equal to 1 because by definition, 0 and 1 are different, and same goes for 1 and 2. And so I can define the statement as a valid statement logically, but it's not a sound statement, or it's not a sound argument. And so the core thing Aristotle was trying to tell us is that you can have a valid argument with all your arguments being valid and all your assumptions based on the assumptions you make. But then if you do not ground it appropriately, your argument might be valid, but wouldn't be sound and wouldn't be realizable in the real world. And so about 2,500 years down along the line, somewhere in the 1930s to 1950s, there was a field of study called symbolic reasoning that was brought up by the AI researchers. And so this symbolic reasoning can also be called symbolic AI or symbolic planning or classical planning or old-fashioned AI or expert systems or numerous other names. What exactly is this? So symbolic planning applies the principles of logical reasoning in solving problems. And in symbolic planning or symbolic reasoning, it essentially describes the world using logical symbols, which they call propositions. And these propositions can either be true or false. And another thing in symbolic planning are actions. And actions essentially change the truth values of these propositions. And so an example could be this Bloxwell domain here. We could describe this Bloxwell domain in terms of propositions using prepositions like on C table, on B table, and on AB. It's a conjunction of all of these symbolic propositions, essentially describe a symbolic representation of this Bloxwell domain. Then an action would be, say, stack AB. And an action always comes with a sort of preconditions, which are essentially propositions that have to be true in order for the action to be executed, and a set of propositions that represent the effects. And these are the changes in the truth values of the propositions once the action is executed. So given this representation, what people who did symbolic planning did was to basically chain a set of these actions and ensure that they are consistent. The chain of these actions would represent a symbolic plan. And so we can tell from what I just described that reasoning happens in the abstract realm, or AI planning people usually call it the lifted realm because it's lifted and not abstract. And so it's lifted and not on the ground. And so in order to execute a plan which is made up of a lifted, in order to execute a plan which is essentially composed in a lifted domain, we have to ground the plan by like bringing it down to the ground. So that's why we call it grounding. And by grounding a plan, you basically supply it with real numbers that enable the plan to actually be executable in the real world. And from the past 15 years in AI and robotics research, we've realized that if you just plan in the lifted domain and then come up with some heuristic approach for grounding each of the symbolic actions in your lifted plan, it doesn't usually work in the real world. It might work for a very specific domain, but in the real world, if you don't consider the continuous grounding values that exist in the real world and just plan in the lifted domain, there's a high probability that the plan you come up with after you ground it later on is not going to be feasible in the real world. And so the main question after all these descriptions is how can we integrate symbolic reasoning and symbol grounding? And you might wonder whether this question is an appropriate question to ask, or an important question to ask. And I asked myself this. And one proof that shows that this question is probably a very reasonable question to ask is none other than from our lab logo. So you actually look at the name of the lab, it's called a Laboratory for Progress, where the GR in progress essentially stands for grounded reasoning. So the fact that this is in the lab's name essentially tells us that we really need to think about how to ground our reasoning in order to get them to be executable in the real world. So this is a very important question, at least based on chat's reasoning. Assuming that
I'm logically valid.
Exactly. Yeah, based on chat's assumptions. Yeah, it's a valid question to ask. And so how can we go about answering this problem? And before we try to answer this question, let's move on to the second principle, which was in the title of this talk, which is mathematical programming. So a mathematical program is basically a class of algebraic methods that prescribe the best way to achieve a given objective while satisfying a set of constraints. And a mathematical program is a very elegant, a general, and a clear way of expressing problems. So folks from the state estimation robotics group, like people who do state estimation robotics, might not actually agree with me, would probably argue in favor of factor graphs or some other form of graphical model. But I mean, I think mathematical programs are much clearer than those ones, because with mathematical programs, there is no ambiguity. It's very clear and elegant. You know exactly what the variables are and what the constraints are working towards. Or the factor graph, you have to like have some extra explanations, and that's too much to think about. So I like mathematical programs more. And another nice thing about mathematical programs is that the person's research community has done a tremendous job in providing some really fast and great open source and commercial service for solving mathematical programs. So suppose you can express your problem in a mathematical program formulation. You could basically just call an off-the-shelf solver to solve it for you to give you some values, some feasible and optimal values, depending on your formulation of the problem. So what is a mathematical program? It's basically an optimization problem. And so an example here is this is an optimization problem that's minimizing a function f of x u, u, with the decision variables being x and u. And so f here is the objective function, and it's subject to some two constraints. So the first constraint is an equality constraint, which is g of x, u equals b. And the second constraint is an inequality constraint. And the type of mathematical program, or the classifications of mathematical program, would basically depend on the forms of each of the functions in this problem. And so if, for instance, f was a linear function, and g and h were all linear equalities and inequalities, then this would be a linear program or a linear optimization problem. However, if f was a quadratic function and g and h were all linear constraints, you would end up with a quadratic program. Or if g and h were quadratic and f was also quadratic, it would be a quadratically constrained quadratic program. And if they're all nonlinear functions, then it would be a nonlinear program. And so the kind of functions or the type of functions that are involved in this mathematical program basically decides the kinds of algorithms you can use to solve it, as well as whether or not you get a global solution or local solution. Yes.
Can you break that down? So what do each of these variables mean?
So x and u are basically placeholders for the decision variables you're trying to optimize for. And f, g, and h are basically functions that act on these variables. And the g function or the g equation is an equality constraint. And h is also an inequality constraint. And I was saying that the type of the functions basically determine the type of mathematical program it is and the kinds of algorithms you can use to solve it.
Well, let me say that I think when you show a slide like this, it makes me a little concerned because I think one stylistic rule that I have is I don't show a variable unless I define that variable. It's that variable is like there's something on the screen that says like.
Oh yeah, that's like the next slide.
I don't know if that maybe a more intuitive, like I think I think that tells me what it's a member of, the set it's a member of, but I don't know if it gives me an intuition, right?
I mean, it's supposed to be a general variable. It could mean anything. So this is like just a general like description of what a mathematical program or an optimization program would look like.
I mean, I should also say, in group meeting, we're not, these aren't meant to be polished slides, and you have to be, so, but I think I want to say, but also, in terms of setting the standards, typically when you show, like, if you want the talk to be intuitive, whenever you show math, like with mathematical italics, you want to introduce each variable one at a time and give a clear intuition for what it means. And so I'd like to make sure that everybody in the room gets what that is, right? So let me ask a few questions on this. What's the difference between X and U?
Oh, I was going to talk about it. That was like the next point.
Well,
Yeah.
before you show that, we'll freeze it right here. So what is? Let's just talk about it. What is X and what is?
All right. So X represents like real number variables, and so it exists in the real number system. And so R of n is basically where n is like the dimensionality. If n is 2, then it's like isn't it 2-dimensional? Or if n is 3, is a 3-dimensional vector. And U also represents integer variables. And so it could also be a vector of integer variables based on the value of n. So if n is 2, then it's a 2-sided vector of integer variables, where integers are negative or positive whole numbers.
Can you give an example where we use X and U? Just a quick example.
So this is supposed to be really, really general. And so, but an example could maybe be, say, if you want to optimize for, say, the number of pieces you want to buy based on the number of people who are going to come into the group, as well as the dietary restrictions and all of that. I guess U could be the number of boxes of pizza. And we want U to be an integer because you can't buy 0.5 pizzas. You always have to buy a whole box of pizza. And so U would always have to be an integer variable. And X could probably be, I don't know, the space of the whole room, or the amount of, I don't know, the area of the room. And so it could be continuous because area is a continuous value. It doesn't have to be integer variable. And then an optimization problem for the F could probably be, I don't know, you want to optimize for the satisfaction of everyone. And so that could be a continuous value you want to optimize for. And you probably want to maximize that as everyone is going to be hungry. But and a G could be an equality constraint. For instance, if you everyone is supposed to get 5 pizzas, the equality constraint would be that that function should be equal to 5, where b is equal to 5. And an inequality constraint could be no one is supposed to eat like more than 6 slices of pizza or something. And so C would probably be 6, and it should be a function that represents the amount of pizza everyone eats.
So wait, so that's what I didn't get. So you're saying that G would represent the number of pizza slices that people would get, which would be 5.
No, D is the number of pizza slices. So G is a function that basically takes in X, which is the space, the size of the area of the room, and U, which is the number of people here. And this is probably a poor example, but
wait, all right, wait,
Make X price.
yeah, I guess X can be the price. Yeah, and we probably want to minimize the price based on the number of people, and U is the number of people, so it's supposed to be an integer value.
I thought U was the number of pizzas.
Or number of pizzas. Yeah.
Okay.
I'll probably have to sit down and like design it probably, but I mean, this actually goes to show you how easy it is to like write a mathematical program. You just have to just.
All right, so coming back. So G is the number of slices that a person would get.
Okay, yeah, let's decide on that. Yeah, G will be G is going to be a function that takes in. G is going to be a function of the price as well as the number of people, and it should be equal to some equality value B, where B could be the number of. B could be. Well, let's think about what it could be. I mean, I have to think of it in the context of like eating pizza here. I guess B could be that, I don't know.
Time to serve the pizza, like how long it takes. That's all
Yeah, and if that's a constant, then yeah, everyone should eat the pizza in 5 minutes or something.
Right.
Yeah, and
So then what's the inequality?
yeah, so the inequality is basically H should not be greater than C. So H,
Costs, like Chad has given us a comfort level budget.
yeah, basically that. Yeah, we can't spend like $500 on food
So
per meter.
so wait, so one of those is for per individual, right? The other is overall cost, right? The overall. So does G apply to each individual, and H apply to the overall system? Or does that, am I inserting something that I shouldn't insert here?
Right, so ideally, so both of them represent the overall because U is supposed to be the total number of people who are going to come in, and X is supposed to be the amount of money you're going to spend.
I think it could be like any constraint you could come up with. Like F is like some function that we've written that is like how happy we all are and we want to maximize it. And H is like you said that Liz can't spend over like $100 on pizza. And G is like Anthony has to eat 3 slices of pizza, otherwise he'll be really sad. So like, I don't know. So maybe that's not a good constraint anyway.
Anthony, you want to add something to that?
I was gonna ask, or sort of ask, or maybe suggest that we think, or is it right to think that B and C are vectors as well?
Yeah, B and C could be vectors. Yeah, it could also be vectors.
So you have like any number of equalities or inequalities.
Yeah. So you can have like a whole list of inequality and a whole list of equality constraints. But then this is just like a general combination of it, just to make sense.
What's the size of that vector?
It's well, it depends because X is size and Z is size M. So it depends on exactly what goes only in the G function.
You don't have to constrain every variable, do you?
No, you don't constrain any
It's just like
every variable.
the inherent constraints that come out of the problem.
Yeah, exactly. And
I think Matthew had something on that.
Are the three equations here supposed to evoke syllogism from the other sides? So like the such that will be like if g of x equals b and h of x u is the same as c, then you want to find that.
I didn't think of it that way. I mean, syllogism was just for like logical stuff. I'm not really applying it here as a mathematical program. So it's like all the logic stuff and this all the math stuff.
He was just trying to tell you a story, I think, right?
Yeah. So in history, like anytime you do logic, you really don't like care about numerical values because you're dealing with abstract stuff. And mathematical programming is you only care about numbers because you're dealing with real stuff. So the whole point of this talk is how do we combine them?
But how do we connect that front end of the story with that? So that may be something.
Yeah, that's going to be after the next section.
The next one, all right, it's coming.
Yeah, it's coming.
Tommy, then Nikhil.
Yeah.
I was just going to say, as much as I'm enjoying the discussion of how best to exactly formulate the most general possible mixed integer optimization problem, I think maybe we should take it offline. Talk for maybe almost kind of about this one slide. It seems like Alphonse's point was just this is what it looks like in general, and let's see where he goes with it.
I respect that point, but we'll disagree. I think it's part of the, here's my logic with this, is that in part of our putting more energy back into the group, I think I have not been as particular about the slides. And I think we have to be just a little bit more careful about how we show this and how we describe it. So we're gonna give Alphonse, I also want people to follow along, because I think we have some people that maybe didn't come from maybe a math degree or something like that. And so we want to make sure that everybody gets it.
In that case, I would suggest indexing the G, A, B, and C, because that way you can at least say that there's an arbitrary in those equations.
Yeah. Interesting. That's a good point. Nikhil, then Jorge.
I had a lot of points, but I actually agree with Tommy. But I was going to say you could view it as a logical problem because the requirements on like constraints themselves are like logical. It's very abstract. Like I understood your point when you make it the difference. Like for our understanding, we should make the distinction.
Yeah, I mean, you can think of it as you could formulate logic as a optimization. That's basically what I do really in the third part of this talk. So I'm just building up to it. But usually people don't really think of mathematical programs in terms of logic. They usually just think about real numeric values.
Yeah, and the second point I was going to make is that you'll often see the constraints specified as matrices, and that's why it could be easier to think about like how B and C are.
But you got the high level point of what it's trying to say.
Yeah, usually when constraints are matrices, it's usually linear constraints.
Oh yeah.
But I want to make G to be a general constraint, okay? So it could either be linear or highly nonlinear or something else.
So let me say that the part of the reason why I'm getting into Alphonse a little bit is because I think we want clarity in some of these, and so we want to be able to discuss it, make sure that everybody has it. So if you have the idea, great. I think it's very helpful to know that those could be matrices. So that gives some insight. But we can move on after Jorge.
Yeah. I mean, this is important because there's going to be lots of optimization problems. So you want to understand the structure.
Yeah.
I just wanted to give another example, not sure if, right? I mean, how to match this to one example or real example or robotics example.
How about this? Let me ask if people understand the idea that Alphonse is talking about. Let's hold off on that. Give you a chance to talk. Do people get this? Feeling comfortable with it? All right.
Can I skip? I'm sorry. I
Sorry.
have a question.
Yes.
I'm
Wait,
sorry
but-
to
so
follow
before you do that, I think also I would say that when you're in a talk, it's appropriate to ask questions in the moment that are clarification questions, so you understand what you're seeing. And then the questions that are philosophical or critiquing or getting into the details, you usually save for the end of the talk. So that's kind of what we're doing. All right, now,
Let me clarify. So what is the, because this is like a general like optimization formulation. Is there a distinction between mathematical programming and just like an optimization problem? Is this just like language that you
Yeah, it's basically the same
chose
thing.
or?
The same thing, but mathematical program sounds more eclectic, sounds more elegant.
Okay.
Yeah, it's basically an optimization problem, but that's like very.
what would the OR people call it? What do you call it, linear program?
Yeah, they have a class called linear program. Actually, they have an integer programming class, so they probably call it mathematical program.
All right,
It's just the robotics folks who call it optimization.
all right, fair.
So, you know, like that.
Yeah,
The
no,
math people call it optimization too. That's the most general term you can have. And then like linear programming or mixed integer programming or all of these things are very specific terms.
A clarifying question. I've always wondered, do you know why is it called programming? What is the program? Or is there a program?
I'll think the programming is basically, it's probably called programming. This is just a guess, because essentially specifying conditions for which your program should, like, if you're going to use a solver, which is a program. This is basically a specification of a problem, as well as all the conditions for which your program should find X values and U values that satisfy all of these. And so I would think that's probably where the name programming came from. But that's just a guess.
can I offer my guess too? Because I don't know for sure. But usually when you're talking about math, you have equalities or inequalities that you're relating to each other, so you're specifying rules. But once you have men or argmen, there's some machine that has to run in order for that to work, to produce that. And so there's some, so you're programming that machine to do this, even if you don't know what that machine is. So that's my guess, my understanding.
All right, any other questions? All right, so usually with quadratic programs or linear programs or whatever, it's usually just the x variable, which is a real number. But there are a class of problems called integer programs, where there's the u variable, which is an integer variable of size, whatever. And they were initially very difficult to solve, but researcher called Alison Harcourt was one of the few people who came up with like very powerful algorithms for solving integer programs. And she came up with a popular branch and bulk algorithm, which is like one of the most intuitive integer programming algorithms of it. So yeah, that's her. She's still alive. She's like 94 or something. So that's very interesting. Right, so I've set up all these phrases for mathematical programming, and that's they have this nice ability to account for numerical constraints as well as to optimize for specific objective functions. And so the question still remains, how do we exploit these unique abilities in performing integrated symbolic reasoning and bounding? And which is basically how can we exploit all of these abilities from like logical reasoning as well as mathematical programming to come up with approaches that can both perform symbolic reasoning as well as command them with continuous variables that satisfy any kind of constraints you give it or optimize for any kind of objective function. So this leads us to the third part of the talk, which is basically a specific talk on a current project I'm working on with Nico and Chad. And then I always change the name of this before we talk, but the name is currently Grounded Task Planning as Mixed Integer Programming. And the goal for this project is basically to develop a symbolic planning approach that is capable of accounting for numerical constraints and optimize for numerical objective function. And the major contributions of this work would be as follows. We propose a new representation of the planned space, and we call this the hybrid file graphs. And the second contribution is we propose an encoding of the hybrid file graphs as a mixed integer convex program, which can then be solved, and the outputs of this would be a grounded plan. This is essentially a plan, symbolic plan that has its continuous parameters filled in, which can actually be executable in the real world. So looking at it from an IO perspective, the inputs is going to be the description of action primitives and planning problem. as well as all the numerical constraints wanted throughout our problem. Output is going to be a plan made up of grounded action sequences. Right. So before we go into the nitty-gritties of this approach, we first present our major contribution, which is basically actions as funnels. And so what is a funnel? Let's go through this thought process. So given an action, we want to represent an action as a funnel. And first thing we know about an action is an action which is probably, which could be either a continuous or discrete action. We'll have some continuous preconditions. And these preconditions could be described in terms of equations, either linear or linear or nonlinear equations or inequalities. So these, let's assume we have all some sort of inequalities or linear equations. These are all linear here, but they could be nonlinear or whichever form.
Question, what space are we looking at?
We're looking at the SET space. So in terms of
what
like
space?
2D space.
So, is it X?
X and Y basically. So
So
think
is
of
it the X from the,
X to be horizontal and Y to be vertical.
and where's you?
Uh,
Coming from the X that you had in the previous slide.
no. This is a different space.
This is a different space.
Yeah, there's a different space. But we can think of all of these, the constraints I'm introducing as two-dimensional constraints.
Can we try to connect it back to that? Yeah, because that's not appropriate to connect.
I'll connect it later on. Yeah, because it's going to be a bit muddled. So you could think of this in isolation, and once we get there, I'll bring all of them together.
Okay,
So we have,
wait, you have a question?
So can we, is any of this visualizing as like what's an action? Or how do I?
oh yeah,
does it
so
connect to this line?
an action is basically anything that has preconditions and effects and dynamics. And so after I build up this whole picture, you have clarity of what it is.
So, okay, I'm gonna stop. So, but I think in general, like forward references are hard to do in a talk because your audience wants you to build up a story that continually goes one on top of the other. And so, this sort of progressively builds up. And so there's discontinuity where you say, all right, this is not related to what I had in the past. And you have to wait for the point that's coming later. That's a little hard for the audience. So maybe you could go back and show the polygon there, and we can try to just flesh it out just a little bit.
Yeah, I try to build like Lord of the Rings, where like there are different people with different backgrounds and they all come together.
Yeah. Well, I mean, so I think it comes down to, so what does this space represent? I think Anthony asked the right question. Said, how do we consider an action in this case?
I'm building up to it. So this is basically just the preconditions of the action. And so it's kind of like building up. So after I finish the whole geometry, that would be an action. So an action has like continuous preconditions and continuous effects and some dynamics. And so I'm building the continuous preconditions and I'm representing them as linear equations or nonlinear equations. And linear equations can be represented as lines. So if you had an equation, like say x plus y equals 5, you could plot it on the 2D xy charts as a line or something. So each of these lines are equations or inequalities.
In state space or action space?
In a state space.
State space.
Yeah.
So in a 2D system and 2D state space.
Yeah, so an action takes you from one state space to another, from one portion of the state space to another portion of the state space.
All right,
Yeah, so you can think of that as what an action is.
great.
So this is the first portion of the state space. And so all of these inequalities, let's call them inequalities. There are a bunch of them, and the intersection of all of these inequalities form this region. I call this region the input region. So this is the input region, and all of these equations are essentially equations of each of the lines that come together to form this polygon, or polyhedron, or polygon. Yeah. So this is the input region, and these are inputs constraints to or the preconditions which you have to satisfy in order for this action to be executed. And then once you have the input region, we also have action dynamics. So you can think of the action dynamics as basically F equals MA or some function that basically tells you, given these inputs, what are the corresponding outputs once you run the function, once you run the inputs through this function. So you can think of this as the dynamics function. So F equals MA is the dynamics function for like actual physics dynamics, Newtonian dynamics. Yeah. And so once you apply the dynamics to all the peripheries of this input region, you basically extend all of them. So once you extend all of these by running the dynamics, we end up with an output region, which is also in 2D space, which represents the region that is outputs after you run each of the inputs through the dynamics. And so this kind of looks like a funnel. And we call this the output region. So the output region also has a set of inequalities that represents that region. Intersection of all of these inequalities represents a region, and this region is the output region. And then we could also have some external constraints, like for instance, some external constraints which could be anything. They could also be in the 2D space. And so this essentially represents actions as funnels.
Why do you have 5 equations on the output, and four equations on the input?
That was also my question, actually. I was wondering how dynamics can give you two equations for one way.
Trying to think of a good explanation for that. So for generality's sake, this is like with what they call the levels of generality. It could either be that both the number of equations on the left and right will be the same. It could just be that your output region, based on the constraints, ends up like the constraints will probably like, even if you look at it geometrically, the constraints actually adds a line to this region. And so we end up with more linear or more constraints or more, the region ends up with more sides than the input region. The output region ends up with more sides than the input region. So you can think of the reason why you have more constraints on the outputs to be an effect of external constraints that are applied to the output region.
So, we've got questions. Jorge, want to go first?
Yeah, so I think maybe this could, these lines that is like, there are like even the idea of a mapping from the input region to the output region. So you have these lines, the connections between the vertices, between these two polygons. I think it's given the idea that it's like a mapping from one region to one, direct mapping. But if you remove these connections, maybe you put an arrow, like a jump arrow, indicating that somehow there is a transformation. In both regions, they have different constraints.
Yeah.
So that's why you have different sets of inequality.
Yeah, that's true. But we also want to represent as a funnel in that all of the space within this funnel that looks like a 3D funnel are all like resultants from our trajectories from the input region to the output region. So you can think of this as a funnel where you take some input region, you apply the dynamics, and then you get some output region. And all of the contents of this funnel are basically valid trajectories using when you apply the action dynamics.
Just to finish, yes. So what I think is basically they can have different constraints, so not necessarily have to be the same.
Yeah, they don't have to be, they have to be one-to-one, because there can be some external constraints that are on the.
And just to finish, one example could be when you have, like, for instance, a threshold, when let's say you have a control signal, but you have a maximum speed. So the speed will just shut the speed, and that will trigger trim the output.
Yeah. So that could be like an external constraint, or you could have like
External constraint.
yeah.
So is the idea that you basically have some higher dimensional space of all of the possible constraints and all the possible states, and that your input region and output region are sort of projections or slices of that?
Yeah. So I guess you could think of it as that. So the entire space is just the entire 2D space, and the input region is basically a subset of the 3D space, and output region is also a subset of the 3D space. And the contents of the funnels is to try to choose from input regions to output region based on the dynamics.
Wait, you said higher dimensional though. Were you expecting it to be,
So I guess, like the way it's visualized now, it looks like there's sort of like you're taking actions, and I guess maybe I'm not quite understanding.
It's all in the same dimension, like it's all in 2D space.
And the constraints themselves are what are changing.
Yeah, there are input constraints and output constraints. That's not constraints.
So is the input region, like, is that a subset of the state space?
Yes.
So it's like valid input state?
Yeah. So all valid inputs are inputs that fall in that region. So the entire state space is the entire like XY space. So you can think of that as a plane. So the entire XY plane is the entire state space, and this region is just a subset of that. And valid inputs are XY coordinates that fall within that region.
Oh, so like, those are is this applied to one specific action?
Yeah, this is just one action.
Okay, so these are like the input, could I think of the input region as like the preconditions?
Yeah, preconditions. And
Okay.
output regions are the state
And
effects.
then that would be like applying this one action to like some state, and that gives you the output
Yes, exactly.
also in state space?
Yeah.
is mapping by vector? Is it one-to-one, like for every point in input, there's a unique, it maps to a unique point in the output.
That'll depend on the dynamics. That'll depend on the dynamics function.
So just to be clear, what you're talking about is the boundary, so the input region is the boundary, let's say the polygon that surrounds all of the possible inputs. And then the output is the boundary that surrounds all possible outputs.
Yeah.
But that doesn't mean you can get any output in that region.
No, this is just an upper bound.
Right. Okay. Anthony?
Okay, I think that maybe answered it. Yeah, 'cause I was gonna ask, like, we have to constrain the action dynamics to like not, split the space into like disjoint subsets, or not subsets, like disjoint sets in the alpha space.
Mm.
But I think if this is like the sort of union of all of those constraints, then I can see how that.
Let me ask this question. Funnels usually get smaller. Right, then will get bigger.
Depends on where side you look at.
There we go. All right. Oh, but
Yeah.
let's
So funnel is just like
yeah.
an idea. So you can have a cylinder which is a funnel. You can think of that as a funnel. A fixable funnel. Right. So this idea of funnels is an extension of the idea of flow tubes, which was introduced by Willie in his 2050 thesis. But this is an extension because it accounts for both linear and nonlinear constraints, as well as present hybrid actions. And so, more formally, a funnel is a versatile representation of hybrid actions. And hybrid actions are actions that can have both discrete and continuous preconditions, as well as discrete and continuous effects. So what do we do with these funnels? We use them to build a hybrid funnel graph. So how do these work? So let's assume at some time step t, the state can be represented by these facts. Or yeah, let's just call them facts. And so each of these, each line represents a fact. So this is a discrete fact, a symbolic fact. I'll call them discrete facts from now onwards. This basically represents the reverse hand is empty. Basically states the reverse hand is empty. So you can have a true value, either true or false. And clear box one is also a fact, which basically says that there is nothing on top of box one. So box one is the top of box one is clear. And it can also have the true value of either true or false. And this is a continuous fact. Let's call them continuous facts.
We'll go over, don't worry about it.
And it's essentially a fact on the robot pose. So let's call the robot pose X, R, and Y. For now, let's just assume it's just continuous. There is some continuous variables. I'll describe all the variables in the next slide. And let's think of these also as just some continuous variables. And so you think of these as the XY position of the robots. You can think of this region as the XY position of the box one. Yeah, so that's the this box basically represents the state level. And then given the state level, all we do is we find all applicable actions in the state level. And applicable actions are actions whose preconditions can be satisfied by the facts in this level. Or in other words, applicable actions are actions whose preconditions are subsets to this set. And so if it has a discrete precondition in a subset, basically means that all of the preconditions of that action are subsets of this whole set. But if it's a continuous precondition, then that would mean that the continuous input region of that funnel intersects this continuous region here, described here by this inequality, and so on and so forth. So that's basically that's basically the definition of an applicable action. And so some of applicable actions. And so for instance, this is an applicable action, which I could call a pick action. So the pick action has a precondition that the hand should be empty, and also that the box should be clear, that the robot should be at some specific pose, or the pose of the robot should, the region of the pose of the robot should basically intersect this region described by this inequality, and the position of the box should also intersect this region described by this inequality. And so this becomes an applicable action, which is called a pick action. I don't want to pick here because I don't want it to be cluttered, but think of this as a pick action. And because it has a discrete effect, it's just the output is just like single point because it has a discrete effect. And another action, applicable action, is the move action. So move only requires that the continuous precondition of move would basically be that the hand should be empty, and the discrete precondition, is that the hand should be empty, and the continuous precondition is that the robot should be, the pose of the robot should intersect some region that was described here. So once you have these, we can then compute the end regions of each of these actions. And before that, there are also other actions we call the no-op actions. So the no operation actions are basically actions that basically do nothing. We just transfer the truth value of that variable from one time step to another time step. So there are two no-op actions for the discrete parts. And there could also be no-op actions for the continuous parts. Depends on the kind of problem. And so once we have all of these, we can then get the end preconditions of each of these actions. So the discrete precondition of the pick action is that the robot is holding the box one. And this 180 is basically just the value is basically maintained across the time step, and step box is also maintained. And the move action essentially is also maintained. Like after you move, your hand will still be empty, and the robot's pose will be in a separate region. So what you're trying to do here is basically trying to build a plant space, which is basically the set of all possible plants in our domain. And so we keep doing the same thing where we get all applicable actions, and then after all applicable actions, basically gets the resulting set of facts. We keep doing this until our goal region is a subset, or our goal sets of preconditions, or our goal conditions are basically a subset of some set of facts. So after we build each green box, which is basically a set of facts, we check whether the goal set conditions are subsets of these facts. And if the answer is true, then we are done building a plant space, or hybrid funnel graph.
So what is f of g in this case?
So f of g is basically a region that describes the robot's that describes a precondition for the robot's pose. And G is basically describing a region for the robot's for the object's box one's pose.
I'm having a hard time understanding why you can project a discrete effect into the continuous space. Like, for example, like,
I don't know how to pick action.
yeah, the pickaxe.
Yeah, so it's just so that we can have actions that have continuous preconditions and discrete effects. So in this case, don't think of it as don't think of it geometrically. Just think of it that this action has these continuous preconditions. For instance, if I want to pick this object, the object should be within the reach of the robots, and so that this could be continuous preconditions. But once the robot holds it, like it's just a discrete action. The pose of the object has not changed.
So basically, it's a convention.
Yeah, it's a convention. So for that instance, it's just a convention, right?
I don't think I'm perfect. So let's start at just at time step T. You have two actions.
Yes, two applicable actions.
All right, what are those actions?
So the first one is a pick action, the second one is a move action.
All right, so what's the difference between pick and move?
So pick essentially has preconditions that the hand should be empty. I should probably the lines are a bit,
Oh, good.
No.
You're fine.
just to make things clear. Yeah. So pick action has these preconditions that the hand should be empty, the box should be clear, the robot should be at some specific pose, and the object should also be at some specific pose.
Okay,
And then once you execute the pick action, the robot is with you, like you've already held it. And so the discrete condition is that you are holding the object.
and what is the state space this is? Is this the box of state space or is this the robot state space?
So here, state space is in the. I talking about the discrete action, the discrete.
The 2D space that the input and the output are defined.
Right. So here, the input is in 2D space, but the output is just a fact. It's just a symbol, basically, that everybody is holding the object, and that's why it's a dot here. This is a convention I used to represent like discrete facts versus continuous.
So is the state space,
So here, the state space is basically
is that with what's in the box, that's the state space? Like, is that where, I think I'm lost here.
so the input here is basically all the continuous constraints.
Uh-huh.
And once you execute this action pick, the result is that the robot is holding a box. And so we represent that as a fact, a discrete fact, which has a truth value of either true or false. And so that's the dot here. It's just a convention to represent discrete facts because discrete facts are not in any 2D space, in numerical space. It's just a
So if the robot's holding the box, let's say I have a robot manipulator or something like that, it can be holding that box in multiple different configurations.
yeah. We could like depending on the problem, you could basically like come up with a different space. Like it is in SE3, like your robot would probably hold the box and hold it like this. But this is just like make it simpler.
So this is like a fact space.
Yeah. This is the fact space.
Okay,
But you could design panels for any kind of action you want. So you got action that's like pull the object and process it up and down. It helps design a function funnel for that.
okay.
So we keep doing all of this, as I said earlier, till the goal conditions are a subset of one of these set of parts. And then you know that you have done, so you have all the possible plans encoded in this hybrid file graph.
Personally, I love this. So like, I don't think my questions, like, I have to make me think. So, for F and G, for these functions, these are the like the inequality constraints in the space of, let's say, the robot pose for X sub R and Y sub R. Then B sub T or B sub 1 is also in the space of X sub R and Y sub R, or it's a vector in the space. So do you need the function F? Like, is that just the identity function? You know what I mean?
Yeah, so it basically describes a region. I guess if you think of the f of t, if it's in 2D space, like this in linear space, the f of t could basically be 5xr plus 3yr. That could be the function f of t, and all of them is less than say 6 or something. And I don't know, I could like a sequence of inequalities that describe the whole region. This is just for like without lots of generality. Yeah, right.
Yeah, another question. So can we think about this, for instance, in the first box, like, so you were talking about mixed integer optimization?
Oh yeah, yeah, we'll get to that.
Yeah,
That's like,
but, well, I mean, the question is about Hansen T and clear box, like Boolean variables, so it's kind
Yeah,
of
yeah,
mixed
yeah.
integer.
yeah, you just have 3 values. Yeah.
Mm.
So we'll get to how to encode this as an MIT. And so this idea was basically inspired by planning graphs, which Anthony actually introduced an example like 2 years ago or something. If you still remember. Yeah. And so with planning graphs, they do something like this, except that with planning graphs, it's all discrete variables. So the innovation here is that we come up with a way of encoding these panels in planning graphs. That we can have like discrete and continuous. Or in this case, all the actions are funnels. So that was an inspiration. So once we have this funnel graph, every funnel graph, we want to encode it as an MICP, mixed integer complex program, and solve it. And before we do that, we have to define our variables. So I should probably do a better job of coming up with unique variable names. I get everything about what I said about x's. So I'm defining a new x here. So x of f comma t is basically a Boolean variable which can take a 1 or 0. And x of f comma t is 1 if affluent f or fact f is true in period t and 0 otherwise. That's the definition of x sub f comma t. And y sub a comma t is also a Boolean variable, which is 1 if an action A is carried out in period t, and it's 0 otherwise. And then we have, so these are the discrete variables or the integer variables, and then we have 2 sets of continuous variables, xr and yr. Should have probably used a different variable name, but anyway, you see xr and yr, they are basically continuous variables, and xr yr basically represents the pose of the robots in xen, so as in this case is SE2, and xb1 yb1 represents the object pose in SE2. So are there any questions? All right.
Wait, I'm trying to parse this. Let me think about it for a second. How many objects do you have?
Just one object.
One robot, one robot in 3 dimensions, 3 spatial dimensions, one object in 3 spatial dimensions.
Let's think of it in two space xy. No theta.
No data, so,
Yeah.
so we kind of, so we're talking about SE2.
SE 1.5.
I'm just gonna think of everything in SE2,
Okay.
and the object is a point object, not, not the
Yeah.
node geometry.
Point object. Yeah. To make
Okay.
things clear and simple.
All right,
All right. So let's get into the.
I have one quick question. So just to confirm, and let me know if I'm wrong or not, but can we think again about this like constraints? So you have the constraints, 2 constraints living on the Boolean space.
No. So
Like,
we'll get to the constraints on the next slide. So these are just variables. I'm just defining the variables and the kinds of values they can have.
okay, so they are not really constraints.
No constraints. The constraints are not coming later. All right. So let's move on to the constraints. So. All right, so the first constraint is this, the initial, I call it the initial value constraint, or the initial conditions constraint. And it's because, and so you realize that T now is 1. represents the first time step, so initial value constraint. So x sub f comma 1 should be equal to 1 if the fluence or the fact f is in the set of initial conditions, and it should be 0 otherwise. The set of initial conditions are given to you, or that's why you give to Adu-Bredu. And x sub f comma big T should be equal to 1 if f is a subset of, if f is a member of the set of co-conditions that like what you want to end up as a co-conditions. So these are the initial and goal constraints. So all of these are constraints now.
Remind me what 1 and T are then?
So this x of f comma T is basically T is the time step, essentially. So 1 basically is the first time step, and big T is the last time step, the final time step.
Okay.
And the next constraint here is I call it the precondition constraint. And basically says that if an action A comma T is, if the action is executed at time T, then its precondition x of f comma T should also be true. And where A is a member of pre-F, so pre-F basically means all of the actions that have the fact F as its precondition. And so this is basically a way of encoding implications, logical implications as inequalities. So if you take it into your program first, it's basically like there's a way of encoding logical inequalities or logical implications as inequalities. So if I have a marker, I could probably test this out. So it basically says that if y is 1, so you think of this as if y is 1, then x should also be 1. But if y is 0, x should be 0. And this holds true based on these constraints, where all of the actions whose preconditions are f, who have f as a precondition, where f is a fact. And this is for all time steps. Now the next constraint is the effect constraint. And this effect constraint basically says that if x sub f comma t plus 1 is true, then all of the actions that have f as an effect, as a positive effect, should also be true. And that's encoded in this inequality. And so let's think of this mathematically. So if x is 1, if this is 1, then the sum of all of these x's should be equal to 1. Because if it's less than 1, then this is not a valid inequality. And if it's less than 1, then this is not a valid inequality. And we won't want one of them to be 1, because all of them cannot be 1, else it's not going to be a valid inequality if this is 1. And this is for all time steps and for all of the fluents. And the next constraint, I call it the mutual exclusion constraints. It basically says that if there are two actions, A and A prime, whose effects cancel out each other, then only one of them can be true. It basically says that this plus this should be less than or equal to 1. Because if this and this is 1, then you're going to get 2 is less than 1, which is not valid. And if both of them are 0, then it's valid. And if one of them is 1 and the other is 0, it's also valid. So this is a way of expressing that exclusivity constraints, logical exclusivity as a linear constraint, linear inequality constraint. And these are actions that who cancel each other's effects. For instance, a pick action and a place action basically cancel each other's effects. So because if you pick an object, then you're holding it, but then if you place it down, you're no more holding it. And so you cancel out both of them through a single time step. And then we have the continuous constraints for our continuous variables for each of the time steps. Given this whole set of constraints, and then plug in an objective function And this objective function basically minimizes the distance the robot has moved for the entire time step. So this is basically just the Euclidean distance.
Can I stop for a second?
Yeah.
I'm gonna take a picture of you in the slide. There we go, awesome. I'm gonna show you this slide, so when you, after you graduate, I'm gonna show you this slide of you talking over a slide of math. And we'll see what you have to say then, all right?
Okay.
Wait, can I post, I'm gonna send it to you on Slack.
So, you know,
So I can I send it to the entire group on Slack, or is it, or just me and you, we'll just be.
oh, you can send it to everyone.
Sure.
Just remember that Slack deletes old messages. So you gotta save it in there permanently.
That's okay, I have it on my phone, I need to back up my phone. All right.
Right, so the objective function is basically if you understand minimizing the Euclidean distance. It basically says that the robot should, you don't want the robot to move very far, or just minimize the distance the robot does move. So this is a quadratic, a mixed integer quadratic program because there are discrete variables x and y, and then there are continuous variables which the robot's pose and the box's pose. And it's quadratic because we have a quadratic objective function, and we are minimizing that function. And so once you have this encoding, we'll then call, we'll then throw it to our very fast mixed integer programming solver like Groby. Groby is like the industry standard because it's really fast. And it's actually free to students. So, and then we would solve it and give us a sequence of actions that are true, as well as the variable values for the continuous variables like the robot's pose for the whole time step, as well as the object pose for the whole time step. And so this would be the output of this whole approach. And you can then execute that grounded plan. So that's our grounded plan, and then execute the grounded plan on the wall. So some preliminary results. So in this video, so the input is basically the description of primitives in the hybrid PDDL format. So I thought about hybrid PDDL in a second. So the inputs are basically a description of primitives, like say pick primitive, place primitive, and move primitive, and as well as some linear constraints that describe the M shape. And so the F and G functions, if you think of, so these are basically like constraints that describe the M function. So you plot these constraints in decimal scale on the graphing, then we end up with the M shape. So given these constraints, these external constraints, as well as the primitives and the description of the goal, we can then get an output from the mixed integer solver. The output is basically a sequence of each of these actions, which each of the continuous parameters like the robot's pose, object pose, that can be used to build them. And the nice thing about this is that if we were to try to do this with a task motion planning algorithm, like say K-lens, PDDL stream, or whatever, like it's probably not going to be either impossible or very hard, because with PDDL stream, with task motion planning approaches, because they specify the goal, the goals and all of that in terms of like in a PDDL file. The goal specification should be a symbolic specification of the goal. They don't really deal with continuous goals as well, or continuous constraints. And so what they usually do is they'll probably like discretize the state space and like represent each single discretization of this 2D space as a square, and then use that to plan. And that's like lots of prerequisites. But using an approach like this, you can just throw in these constraints, these equality and inequality constraints, as well as give it some primitives, and then the robot can be able to do cool geometric block building stuff like block building tasks like these.
Do you run the optimization once? And
Yes.
Then you get the entire plan, and then we're seeing the plan that's executed.
Yes.
But I thought PDL stream was doing replan.
Yeah, PDL stream, it's, oh, this is not PDL stream, this is like average,
Yeah.
but with PDL stream, yeah, what it does is, no, the replanning is like delete PDL stream, that's like
I see.
using PDL stream on like actually observable space, but PDL stream is just one slide. Well, I think it does it multiple times, but then what it does is, I can go into it, but it basically like samples values and checks if they are valid, if they are not valid, and then sample new values and come up with a new plan, and that's that like multiple times.
You have a question?
And
I just had a question. So looking at your visualization, it looks like often after the robot places a box, it goes into the middle and kind of. flips
yeah, it's
around.
just those are just like me being lazy and not coding the primitives correctly. But
Okay,
this was just like proof of concept stuff.
okay. Yeah, I was just wondering if that was like a
Yeah,
bug or like if it was.
yeah, it's mostly a bug. And this is actually digits. If you can, this is digit from the top down. And this was just a proof of concept. And the controller is basically a P controller. That's why it like speeds up and slows down. But there are ways to improve this like a whole amount. This was just proof of concept. See,
How do you, like, is this like a optimal plan? Like, how do you measure the goodness of the plan? Because it seems to just be kind of, it's not like going to the closest box necessarily or anything.
yeah, it's just doing it sequentially.
But that's not his point. That's not, his point is that you can express the goal with that shape, right?
Uh-huh.
And then, and then you just have a collection of actions until you get some plan. You're not really specifying whether that plan's optimal or not, but you're able to define the sequence of actions. Or just, there is a min in there, right?
Yeah, the min is for like for each time step, you basically want to get like the shortest robot distance from like
Like with this,
box to the goal box.
But but this isn't the min plan, right?
Yeah, it's not a min plan. So this was a very rough first take that I implemented this algorithm or something that looks meaningful. But
Is that because of primitives or because of the plan?
yeah, like why doesn't it get the closest box? or something?
so it could be an artifact of the primitives themselves, or it can also be how I encoded it currently. And so currently what I'm working on is to make it much more general and make it much more general, because currently this implementation is very problem specific and I don't really read from an HDL. I basically just like encode all of these right in the code. But the goal is that we come up with a more general description where the algorithm will just read all the constraints and stuff from the code and then come up with action sequences that satisfy the goal.
What are you primitive?
So pick please move. So pick is basically the robots picks the objects and objects that attach the robot's body.
Art. Cameron, got a question.
How are you describing the robot environment, like where the once the forms are placed? Are you telling it where these blocks are?
So the boxes are basically just have the 2D positions of the box, and those are part of the inputs to the other part of the problem description.
The actor you. I'm just kidding. I'll take it back. I'm sorry.
So you mentioned earlier I'm a little confused. Is it optimizing over the entire plan? Like, is the sort of the minimization occurring over the entire length of the plan or for specific actions being sequenced?
So I could encode the objective function differently, but currently it's basically minimizing for, it minimizes for the entire plan, but then the differences are based on like consistent how robot poses in like subsequent time steps.
So sort of, it's minimizing the total distance traveled.
Yeah, but then basically.
Can you go back? One slide. Can we go back to Cameron's question?
Wait, camera?
Yeah, so I think you were asking, where the locations of all the blocks? Does that fit into here somewhere? There,
Yeah, so those are just those are the initial positions of all the blocks.
which one is that?
So it's let's see. So XRT and YRT are basically the flows of the block like in subsequent time steps. But the initial flows of the blocks would probably be like XB1, XB11 or YB11. That's like at time step 1. Where objects are, where the boxes are.
Are the fluids defined over the locations of the boxes?
So,
Is that
yeah,
incorrect?
there are continuous fluents and there are discrete fluents. So XF and YA, XFT and YAT are basically the discrete ones. And then the continuous ones are the XR1, XRT, YRT, XRT, and XRT. So the other positions of all the blocks at the initial states are all like XP11 or YB11 and YB1 is the extra positions.
I think you lost me there for a second. So XR defines the position, XR and YR define the position of a particular block,
Yes. No, XR and YR position of the robot.
position of the robot.
Yeah, and XP, YB position of the block.
I don't see that.
Their arguments of G.
It's right at the bottom.
I see. And B is an index over all the blocks.
So this is just for one block.
That's
And,
the one.
and Zero is going to do a bunch of blocks. We just do XP1, XP2, XP3, and so on and so forth.
And so you have so you just, those are just constraints that enumerate out.
Yes.
So you can imagine that, like, you can see the screen go all the way down.
Yeah. You have like other blocks. I made this, even though this looks a lot, it's just for one block. You go to other blocks. I think once I actually encode a bunch of blocks, there are like lots of constraints, like the other 200. So,
Can I answer your question, Cameron?
Yep.
Nikhil, you have a question? No? Okay.
all right, so these are just like, these are preliminary proof of concepts, but I'm currently developing a bunch of packages in order to make this more general, because I think this has value and I hope to work on it for a while. So the first is westbrook.jl, which is named in honor of Russell Westbrook. If you're a basketball fan, I don't know if you get a joke, but so he misses a lot of shots, and so they call it a break in basketball lingo. And so Westbrook basically means he's a terrible shooter. And it's basically like the robots building blocks using bricks. And HPL is basically, I'm also working on an extension of PDDL, which can with which you can encode continuous constraints. Because currently PDDL can only encode like symbolic fluents, but if you want to use it with HPL.jl, we come up with a way of like encoding continuous constraints in the planning problem. And also a package for hybrid funnel graphs for building up a hybrid funnel graph from an HPL description. And then MITOMP is the main algorithm implementation. So all of these depends on all of these algorithms. And the reason why I'm doing this is I want to make this as general as possible so that I can build up on it as well as other people can also use it. So that's it. So this is the last part of my talk. Basically, moonshot ideas or ideas I was working on some kind of this, and which will hopefully build up to my PhD thesis. So the first idea is probably what Chad has been thinking about earlier this talk is we are making a lot of assumptions about full observability, that we know all the symbolic fluents and all of that, but in the real world there's lots of partial observability, and you have to have a way of representing uncertainty when you're performing task planning. And so how can we represent uncertainty when actually solving mixed integer programs? And there are some ways to do that, especially with and what we really want to do is represent and propagate uncertainty when modeling and solving mixed integer programs. And one of the famous algorithms for solving mixed integer programs is a branching bound, and it basically uses a graphic formation to actually solve a mixed integer program. So there is some promise of incorporating bleak propagation in that, or some form of probabilistic inference, where like we can account for uncertainty in every step of the branch and bound process, and come up with results that account for uncertainty as well as like uncertainty in the reverse belief of the law. So this is something I'm thinking of working on. I'm thinking of calling it PIMP.jl.
Please don't call that that. Please don't.
Oops.
Oh my God. I just want to, I will admit, I got the West brick thing, West brick thing immediately. I was just like, all right, I realized how, how my jokes may not hit because I got that one. But Pip is like, oh my goodness, that's a Michigan Daily story we have. My goodness.
I mean, if it's good enough, like people would overlook the name. And
P-Myth I like a little bit better, but
it's not as catchy. So that's the first page idea I have, and I hope you're working on this. I'm glad after this one. And the second initial idea is a very, should probably be, I don't know, it's a very small far-fetched, and the idea is to learn optimal primitives for robot task planning. Because all the primitives I discussed here, the 15 place primitives, are basically simple primitives I designed by hand. But I need to want to get robots to work in the real world. They would have to be capable of designing their own primitives or learning their own primitives. So how can we get robots to learn these primitives with which we can then use to perform symbolic planning that accounts for numerical constraints or grounded symbolic planning? And this is a subset of the very contentious topic amongst the AI community. And so on one faction, there are the symbolists, and on the other faction, there are the connectionists. And so the symbolists would be someone like Marvin Minsky, who likes to think of AI as basically symbol manipulation and really hates connectionists. And the first connectionist was a guy called Frank Rosenblatt, and he was the developer of the first neural network. So this was back in the day. And modern symbolist versus connectionist, the symbolist could be, say, think of, say, Gary Marcus as a symbolist, because he's always like thinking of like using symbolic planning as AI, because symbolic planning was very powerful where people disregarded it once without deeper on it. And so we learn, basically learning everything and not using symbols for anything. And the more contemporary connectionist would be, say, the theory neural winners. And the main reason why there's this faction in the AI community is both of these methods have their own nice properties. So with symbols, as I've talked about throughout this talk, symbols are explainable with first order logic. And so once you have a decision made by a symbolic planner, you can actually reason about the decisions made or the plan that has come out, and you know that this actually makes sense because based on the assumptions you make using syllogism and first order logic, this is actually a sensible plan. And symbols are not data hungry, like you don't really need to feed in any data or train anything, you just design the symbols and use them to reason. But the downside is that you have to actually design those representations. And so that has led to the more recent uptake of neural networks. And neural networks are not explainable, and they're also data hungry. And but the nice thing is that they learn representation from data. You don't really design your own representations yourself. And so the ideal thing to do is basically to come up with a way of unifying both the symbolist ideas as well as the connectionist ideas. And that's what's currently called a neurosymbolic AI. Neurosymbolic AI has seen some uptake in the last, like, I think 4 years or so. So the folks from IBM's MIT, Watson, and a lot, that's like David Cox and sometimes Joshua Tenenbaum. They come with a bunch of papers on neurosymbolic AI. And they've got to do some cool things, but it's not really on the level where it's actually applicable in robot problems, or like applicable in the kind of task we care about in robotics. And so the hope is that we'll be able to extend my approach, or able to work on an approach to mostly learn the right symbols that can be used for task planning. We can then have agents that can autonomously and explainably perform all the useful tasks we want to perform in the world. So that's something else I want to work on. And that's it. Thank you.
Go for it.
So on the slide, like the